Hello, I would like to start this lecture off by reminding you, be a good comrade. That's terrible. Also, I keep going in and out of focus. That's actually really happening. That's not the camera's fault. That's me. I've just been really out of focus lately. Like, just keep blurry. It's pretty bad. Okay, well, anyways. Let's forget that happened, and then I posted that on YouTube. We're going to be talking about Chapter 2, resistance-only circuits. Okay. Now, first of all, you have a reading assignment. It is due next week. That is, whoa. Yeah, I may need to move this camera back. If this keeps doing that, because I don't really want it to keep doing that. I don't want to expose how unfocused I am. Gross. Problem is, it's me moving. Me moving is doing this. I should like change my lighting. That would actually fix a lot. And I can do that pretty easily. Down. You're gonna see a little back end view of your instructor in the wild. As I said, we're moving on into resistive only circuits. Now, what does it mean for a circuit to be resistance only? Well, what it means is that the only components that we have are resistors, and the importance to that is that resistors abide by Ohm's law, and that's something that we can consistently count on for those components, is that they are linear relationships between voltage and current. Now, we did talk about the equations for capacitance and the equations for inductance. Yes, those equations are not linear. Those equations actually have a oh, that's oddly bright. I should move that over here. Those equations actually have an integral relationship between voltage and current. So what you end up with is, hopefully I'm not out of focus anymore. What you end up with in non-resistive oldie circuits is you end up with really weird relationships, which we are going to get into later on in this chat. But for now, we're going to be talking about resistance-only circuits. And the first thing that we want to talk about today is parallel versus series circuits. I know this is actually a Chapter 1 topic, but I like presenting it now because, well, why not? So we're talking about the difference between a parallel and a series circuit. Let's define both of them. In series, if two components are said to be in series, then what you can say is that the output of one component is the input to another. Okay? So, for example, if we have a resistor like this, and then a resistor like this, here's positive and negative end, here's positive and negative end. You'll notice that the negative end of this resistor and the positive end of the next resistor are both connected to the same node. Basically what that says is that these are in series, because the output of this one, if we have current flowing from positive to negative, and we have current flowing from positive to negative, the output of this one will feed into the output of the input to this one, and so any current that goes through will go through both of these. Okay, so now we'll also define parallel. In series, the output of one is the input to another. In parallel, the inputs and outputs of components are at the same node. And I should say nodes. Okay, so for example, if I have a node here, and then I have a resistor that comes out of it, and then goes into a node, and then I have another resistor that comes out of this node and goes into that same node. These are now said to be in parallel. You'll notice the positive ends both touch the same node, and the negative ends both touch the same node. So really, a lot of this analysis of whether or not it's series or parallel is all based on where the positive and negative signs lie. If the positive signs and the negative signs align such that they're on the same nodes, that's in parallel. If the negative touches the positive end, then at the same node, then they're in series. So just another way of thinking about that. Now there are some implications to parallel versus series. And this is something that I think warrants a little bit of a discussion for this course. Now when it comes to resistance-only circuits, let's say I'm going to draw an example here. And here we have a parallel set of resistors. I'm going to go ahead and label the nodes. This will be 1, this will be 2, and this down here will be 3. We'll go ahead and put a ground symbol here. All the ground symbol means is that like you would have a wire connected to here that would go to touch ground traditionally. So that this means that there's no charge buildup. Yes, it is possible to siphon charges out of the ground, believe it or not. Yes, it is possible to actually get current to flow backward out of the ground, but the goal here is in most systems, what you want to do is you want to force this to stay at a very certain voltage. And the voltage of the ground is considered to be 0, even though in reality it actually isn't ever 0. The whole lightning strikes that happen is because ground is not at 0. It only takes a few excess charges on a certain region for the voltage to increase dramatically. We don't actually know what the voltage is anywhere, really. Most of our voltage measurements are relative. Like here, we have a relative measurement of the battery. We touch one end here, we touch one end here. We just know that this point is X number of volts higher than this one. We don't actually know what the real absolute voltage is at 0.3. But that's a discussion for a different day. So here we have this resistor is in series with these resistors. How do we know that? Because the positive end and the negative end here, the negative end leads into the positive end of both of these, and both of these have nodes connected to the positive end and node connected to the negative end. Here, 3 is the negative end, 2 is the positive end. Okay. One of the analytical tools that I like to use to just show students at the very beginning is to create a component table. The component tables are, I don't do these a lot because it's kind of a waste of time, if I'm honest. But it's a good way of teaching how do we understand series versus parallel here. So here you write out your components. You write out the nodes where they're connected to, start node, end node. And then I also like to write out what loops they are associated with. So here, let's say this is R1, R2, R3. Okay, so we'll have components R1, R2, and R3. Now the start nodes, it's just where's the positive end, okay? Positive end of R1 is connected to node 1. The negative end of R1 is connected to node 2. The positive end of R2 is connected to node 2. The negative end of R2 is connected to node 3. The positive end of R3 is connected to node 2. And the negative end is connected to node 3. So nothing too groundbreaking here. It's just a little bit of organization. Now we start talking loops. Here we'll call this loop 1. And then here we'll call this loop 2. Okay. Now R1 is positive in loop 1. R2 is also positive in loop 1 because as you go clockwise around, it goes to the positive end, to the negative end. So, but you'll also notice that if in this loop, it's a negative loop 2. It's negative in loop 2. And then over here, it's positive in loop 2. Okay, so now what this is going to allow us to do is basically, this tells us a couple of things. Here, these say what KCl values are associated with them. Here, this one says what KVL values are associated with them. So if I go to node 1, everywhere where I see a node 1 here, I should see R1. Okay, and we also didn't throw in VS, which I should have done. But VS is another component. It starts at node 3, which is actually the negative end, and goes to node 1. So here, because it's a source voltage, we're just going to go ahead and flip that. Otherwise, we could write it, I guess we could write it backwards. I hate doing that, but because here's the positive end, here's the negative end. Okay, and just have to remember that since this is a source voltage, it's forcing current to flow from the negative end to the positive end, whereas all of these being passive have current flowing from the positive end to the negative end. And here, this is also negative in loop 1. Okay, so we can take these three components that say loop 1, and we can basically generate our KVL equations. Okay, for loop 1, we have VS minus VS plus VR1 plus VR2 is equal to 0. And then for loop 2, we can say minus VR2 plus VR3 is equal to 0. Those are our two KVL equations. And then if you go to KCl, for node 1, here, node 1 has these two components. So we have IS is equal to IR1. For node 2, we have IR1 is equal to IR2 plus IR3. And then for node 3, we have IR2 plus IR3 is equal to IS. Okay. KVL and KCl equations. This is, we've talked about this already. This is going to get old very quickly because we're going to use these all the time. Now you'll notice that this information is already down here in the component table. But we can take some of this and glean some information about series and parallel here. Okay, first of all, we know these two are in parallel. Why? Because the positive ends and the negative ends touch the same nodes. Positive end is 2, negative end is 3. This is the indicator right here that these components are in fact parallel. Okay. Now the beauty of this is what you end up with is anytime you have components that are in parallel, you end up with multiple components that show up in the KCl equations there, because that's what happens when components are in parallel, is you have a split in junction. Now, on the flip end of that, anytime you have components in parallel, what ends up happening is, instead of it showing up in one equation here, like neither of these equations show that they're in parallel. Well, you could argue that that one does, but really, you end up with two loops, an inner loop and an outer loop, and neither of them contains both components unless you actually specifically just do that pane. The way that this shows up here is that you end up with multiple equations that have the same variable. You end up with components that end up in multiple loops, okay? And this is another sign that it's in parallel. Here you only have one loop that most other components are in, but you do have this component is inside of two loops. That's another sign that it's in parallel. Here in series, what you'll see for these two components right here are in series. Because they're in series, you end up with this relationship right here, where one is equal to another. Okay, and you'll also see that because they are in series, they both show up in the loop equations together. If we don't have one, we don't have the other because they're in series. They have to be in a loop together. Here, there is no way to draw any of the loops in this system without including both Vs and R1, or neither of them, okay? So that's a sign that they're in series, is that they basically come as a package. If they're in a loop, they're together, okay? In a series relationship, that there kind of has to be that way. And that's because all of the current that comes out of the source goes into R1. Because these are in series, there's no place else for current to go. Here at node 1, being in series, all of the current coming out of the source has to go into node 1, which then has no other place to go except into R1. So being in series, these are always going to have the same current through both components. That is a critical note. I can't say that enough. Series components always have the same currents. Okay? Now, what if there was another piece coming in here like that? Well, technically, then, yes, they are still in series, but you have another direction for currents to go outside of that. Like if this was, technically, these two components are still in series because the output of this one is the input to this one, but it's also the output of this one is the input to this one. You can collapse all these by you doing an equivalent resistance, bringing them together, and ultimately, then this and an equivalent resistor would be in series. So just keep that in mind. This relationship right here is indicative that they're in series, and it's one of the most critical aspects of this entire circuit. The flip end of this is because these are in parallel, we end up with this relationship right here. We have one loop equation that says both of these have the same voltage. So here, these two components are in series. I'm going to erase my addition. These two components are in series, which means they have the same current. These two components are in parallel, which means they have the same voltage. Now, why is that? Well, because of KVL, because of that relationship, this has to be true. Both components start at the same node and end at the same node. And because they start and end at the same node, it's like, if you start at the top of the mountain and end at the bottom of the mountain, you travel the same distance. It doesn't matter what route you take to get there. The displacement is the same. Okay? Here, the energy distance, the energy drop is the same. You still lose the same altitude here because it's between the same nodes. Every node is at a fixed voltage at a certain time. So every nodal voltage is a function of time, and at some time t, it is at some voltage. You don't have two different voltages at the same node. It's one voltage, and everything connected to that node is at the same voltage. Okay, so that means the negative end of this component, the positive end here, all of them are at the same voltage because they're all connected by wires. Here the negative end and the negative end and the negative end of the source are all connected through wires. They're all at the same voltage too. And if we connect it directly to ground, we can then comfortably say that that is the same voltage as the local ground. So that's just kind of how we have to deal with this. Now this table shows us, again, these two are in parallel. These two are in series because the 1 and 3, 1 and 2, 3 goes to 1, 1 goes to 2. There's only two ones on this table, which means there's only one input, one output of that node. So just an example. We're going to go ahead and jump into another example and talk about series and parallel again. Again, reminder, the whole goal of this discussion is to be able to identify series versus parallel, be able to figure out what they are, because they do have those very interesting relationships. Parallel components are at the same voltage. Series components are at the same current. They have the same current flowing through them. So for our next example, this one's going to get a little bit more in depth. So here we've got positive and negative. Here this is a voltage-driven source. We're going to go ahead and go ahead and do something like this. This will be R1, this will be R2, R3, R4, R5, and R6. Okay, I'm going to go ahead and identify nodes. I like number 1 being immediately out of the top of the source voltage. 2, 3, 4, and 5. We'll go ahead and ground the negative end of the source voltage. And now we'll identify our loops. We'll call this loop 1, this will be loop 2, and this will be loop 3. So if we go ahead and write out our component table, if that's any help to you at all, here we'll need to identify negative and positive ends. Positive, minus, positive, minus, positive, minus, positive, minus, positive, minus. Now this is kind of gross, but we can work with it. So for our components, and then we got our pos node, we got our neg node, and then we got our loops. And this is basically just going to help us write our Kvl and Kcl equations again. It's another way of understanding that. If you can write Kvl and Kcl without them, awesome. If you can understand series and parallel without this table, go for it. I will only use this table for a few lectures just to identify, just to help you see what is series and what is parallel here. Okay, so here we'll start with component, we'll start with Vs this time. Vs, the negative node is 5, and the positive node is 1, and it's in loop 2, and it's positive in loop 2. Nope, it's negative in loop 2. Okay, it's not in loop 1. In loop 1, it only touches these 3 components. If I were to shade the interior of loop 1, it would only end up touching those 3 resistors. If I shade the interior here, it's going to touch Vs, R1, R4, R5. If I shade the interior here, it's only going to touch R5 and R6. Okay, so Vs is only inside of loop 2. We'll include R1. R1 now is positive in loop 2, but starts at node 1, ends at node 3. As I said, it's positive in loop 2 because as we go around clockwise, it goes from the positive node to the negative node, indicating that the current through that item is positive. It also goes through L loop 1, but it goes backward because if we go clockwise around this loop, it's going to start at the negative node and end at the positive node. So this is a plus L2 minus L1. Okay, then we can go to R2. R2 only touches one loop, and that is L1, and it is positive in loop 1. Here the positive node is 1, the negative node is 2. So, and it's positive node 1. Here, R3 is a very similar situation. It starts at 2, ends at 3, and it is positive in L1. And talk about R4. R4 only touches one loop and it's L2, and that is positive in L2. It starts at 3 and ends at 4. And we talk R5. R5 here touches loop 2 and loop 3. It's kind of between both of those loops. And it starts at 4 and ends at 5. It is positive in loop 2, and it is negative in loop 3. Now, R6 only touches one loop, that is L3. It also starts at 4, ends at 5, and it is positive in loop 3. So that's all of our equations here that we have. We can now write our Kvl and Kcl equations out from these. And notice we only have 3 loops. From this, we can say, okay, well, let's write Kvl out first. So we'll start with loop 1. In loop 1, what you have is you have 3 components. R1 is the negative one. R2 and R3 are both positive. So you have negative VR1 plus VR2 plus VR3 is equal to 0. Okay? Now if we rearrange this equation, what you end up with is VR1 is equal to VR2 plus VR3. Now, this is indicative that the components are parallel. Here, VR1 is in parallel with both VR2 and R3, which means if we can figure out an equivalent resistance here, they will basically be in parallel. R1 would be in parallel with an equivalent resistance that equals R2 and R3. Now we're not going to get into equivalent resistance until the next lecture, but that's just something to keep in mind. For loop 2, here we have 1, 2, 3, 4 components. So what we end up with is negative Vs plus VR1 plus VR4 plus VR5 is equal to 0. Okay? And then for loop 3, what we end up with is here you've got VR5 and VR6, so negative VR5 plus VR6 is equal to 0. Okay, so that's Kvl. Our Kcl equations, because we have 5 nodes, I'm going to write them over here. Kcl, node 1, what we have is at node 1, there's 1 input, 2 outputs, so you have IS is equal to IR1 plus IR2. At node 2, what you have is IR2, which is the incoming one, is equal to IR3. Again, this is indicative that they are in series because the current coming out of one is equal to the current going into another. Anytime you have this type of relationship, they are in series. Okay? Anytime you have this type of relationship, they are in parallel. Similarly, you have this type of relationship, VR5 is equal to VR6. They are also in parallel. We can see that these components are in fact in parallel. For node 3, what we have here is there's 2 inputs, 1 output. So you have IR3 plus IR1 is equal to IR4. For node 4, you have 1 input, 2 outputs. IR4 is equal to IR5 plus IR6. And then for node 5, you have 2 inputs, 1 output. IR5 plus IR6 is equal to IS. Okay, so that's the beauty of all of this together. We see it's flowing nicely. We can look in here and say these 2 components are in series. This is in parallel with these 2 components in series. All of this is in series with R4. This is in series with these 2 in parallel. These 2 are in parallel. So as we go into our next lecture and we start talking about equivalent resistances, because this isn't pretty, you know, like we know this is in parallel with that series of equations. What we would do for our first step when it comes to an equivalent resistance is we would combine these so that we can have a nice, true parallel set where we have them starting and ending at the same nodes. Here, this starts at node 3 and 1 ends at node 3. Well, for R2, it starts at node 1 and ends at node 2, which means this does not have the same voltage as R2. It doesn't. The voltage across R1 is equal to the total voltage across both R2 and R3. Why is that? Well, we get this equation that says that. But why is this true? Well, it's because there is a certain voltage drop here. You know, this is like if you go straight down the mountain versus if you stop halfway on the mountain and get a churro. Okay? That churro is kind of important. But that churro doesn't happen at the bottom of the mountain. It happens midway up the mountain. So you haven't gone all the way to the bottom of the mountain, which is R1 distance. You haven't gone all the way to the bottom of the mountain. You've only gone halfway down the mountain to get the churro. And you get the churro and you finish off the rest of the mountain. Hopefully a little happier than you were when you first started. Churros should bring happiness. If you or a loved one has a churro that's bringing you sadness, please contact thereishope.com/churro. All right, we're going to go ahead and move on to the next lecture. In the next lecture, we're going to be talking about equivalent resistances. So